Welcome to part B of chapter 1 lecture recording. This is going to be a short lecture. We have only a few sections to wrap up chapter 1. Please have a pen and a piece of paper where you can make your road notes as usual. I will share my screen and my whiteboard will be on the right side of your screen, and the PowerPoint slides will be on the left side. This is what I intend to cover in part P, the unit of measurement, reliability of measurement, solving chemical problems, and lastly, we'll look at how to interpret and analyze the data. To start off with, in section 1.6, measurement. When we talk about the measurement, a measurement consists of two things. All right, measurement. I defined this earlier on. A measurement consists of a unit plus a number, or a number plus a unit, whichever way you look at. E.g., 10.0 grams. There is a number and there is a unit. This is a unit. Without the unit tied to a number, a measurement will just be a meaningless number. So remember, in the lab, always include the unit of measurement unless you are given in the data sheet. In chemistry units, that is the standard quantities used to specify measurement, are always critical. I will share some of the real life situation where it has turned out to be catastrophic situation where there were loss of life simply because of omitting unit of measurement. There are three, even though here two most common units of measurement, we have three units of measurement. You should draw a parallel. I will show you just few physical quantities we measure using the three systems. All right, so here systems of measurement. There is the physical quantity we measure, length in metric. There is English, and then there is the SI, System International. There are three systems of measurement. You see on one PowerPoint slide, the metric system. When we say length, we use, I'll say here, meter, abbreviated M. In English, this is what we always use at home. Miles, it could be yards, all right? It could be inches and so forth. These are units of measurement in English. And then we have here kilometer. You cannot see kilometer. There are three systems of measurement. The other quantity here is volume. Wherever we are measuring volume, you can talk about the in metric. We use liter. Here it could be fluid ounces, all right? It could be in gallons. And here, meter cubic. So not all just what you see or what you come across in any Gen Chem 1 text doesn't, or just, there is a parallel between the three systems which you should be able to draw. English, mainly used in the United States. You are familiar with gallons. Whenever you visit the gas station to fill up your gas tank, they pump this spent gasoline in gallons. Fluid ounces, all right? Latest, this is the metric we use in the lab. Mostly it's used around the world, and they have different units. Sandys use SI unit. This is the System International. SI, you need to know what it stands for. This stands for System International. Before this system was arrived at, if you recall if you are asked how tall are you, we use feet, 5 feet, 6 feet, and so forth. It started way back when they started measurement. They used to use king's foot. The length of the foot determined the length of, if you want to buy a material, it was a standard. So you could imagine if a king was small and she has a small foot, all right, it's gonna be like a ripple if we are doing trade for that matter. So a scientist or a group of scientists spent about 10 years to come up with a uniform system we call System International, which is based on the metric system, abbreviated SI. We'll see the 7 units for SI on table 1.1, pace unit, length, M for meter, kilogram, second for time, temperature, and so forth. You need to remember mostly what you come across in the lab is length, mass, time, temperature, and probably also we're gonna talk about the mole, but rarely will you see the electric current and luminescence. But you need to know there are 7 phase units used in System International. I will not go in detail or spend more time, but you need to know that wherever we're measuring length, we use the meter as the pace unit. Originally, it was defined as the distance from the North Pole to the equator, which was 1/10 million of the distance from the equator to the North Pole. So this was, if this is the Earth, this is the equator. What is this distance here? It is 1/10,000, 10 million from the North Pole. If this is the North Pole, all right, we talk about the meter. In comparison to Mars, this is just a unit for measuring mass kilogram in System International. There will be some conversion factors you will have to derive. 1 kg equals 2.2 pounds. Down the line, 2.205 pounds. Down the line, you'll be required to convert unit of measurement from 1 unit to another unit using dimensional analysis, which we'll be covering shortly. This is an equivalent statement for other mass measurement. You may have other different units. This just represents what you are familiar with. You have taken masses in the lab using palms, okay, and different scales have different units. What I've highlighted here on this slide is the difference between mass and weight. Mass is defined as the amount of matter in an object. Okay? It's the amount of matter, the quantity of matter in an object in comparison to weight, which is the gravitational pull acting on matter. It is the gravitational force acting on matter. Quite often, we think or we interchangeably use those terms, but that shouldn't be the case. You need to differentiate between mass and weight. The third most common physical quantity you will encounter in lab is time measurement, and in SI we use seconds. Sometimes you may collect data by keeping track of time in minutes or probably in hours. Okay, in hours, and the SI unit for that is second. We are not going to go in details, or no one will ask you about the definition of a second, all right? Just to give you how this second was arrived. It's defined precisely as the duration of 1, 2, 3. It look like 9 trillion, all right? Periods of radiation emitted from a certain transition in cesium-133. It's an isotope of cesium. Temperature measurement, we use Kelvin in SI unit. Of course, in the lab, you will use degrees Celsius. We have other units such as Kelvin. This stands for Kelvin, which you know, and this one is degrees Celsius. Degrees Celsius, Kelvin. And we have also degrees Fahrenheit, which we will see momentarily. Please remember that Kelvin is the SI. This is the SI unit for measuring the temperature, Let's see the temperature measurement. I've shown you these 3 units. You need to be able to convert from one system to the other system. In other words, temperature conversion from degrees Celsius to Kelvin, from Kelvin to Fahrenheit, and so forth. This is the name of a person who came up with the device, the thermometer, for measuring the temperature. We use also Fahrenheit. What I want to show you is the 3 scales: Fahrenheit, Celsius, and Kelvin. What you see here is, let me just blow up this so that you can see clearly. What you see here is the temperature measurement of boiling point for water and freezing point for water. We are familiar with the degrees Celsius. It freezes at 0 degrees Celsius and boils at 100 degrees, but in Fahrenheit, 212, freezing point 32 degrees Fahrenheit, and in Kelvin scale. There is an equation here which I want you to learn. This summarizes how to convert temperature. Let's say degrees Celsius to Kelvin, all right? Which means Kelvin equals to 273.15 plus the degrees Celsius. This is an equation you need to remember in converting the, sorry about that, let me just share my screen. This is what I was writing down, that if you want to change the temperature from degrees Celsius to Kelvin, the equation, let's call this equation 1. Equation 1, given the temperature in degrees Celsius, you add 273, which is this equation. So changing degrees Celsius to Kelvin, 273 plus 1.15. Now, degrees Fahrenheit, or degrees Celsius to degrees Fahrenheit. This is converting from degrees Celsius to degrees Fahrenheit. We will rearrange these equations. So in other words, if you want degrees Fahrenheit, please use this parentheses 1.8. It's an equation you have here, which is 9/5 times what you are given degrees Celsius plus 32, which is part of the equation. This part of the equation, we can have this is equation 2. I will label this as equation 2. So always, either you have to find or you are given. In other words, what you see here is given the temperature in degrees Celsius converted to degrees Fahrenheit, your setup will be 1.8 times the given temperature in degrees Celsius plus 32. And of course, you can rearrange the other one. Let's say Kelvin to degrees Celsius, which means degrees Celsius is given by Kelvin. minus 273.15. What we are doing is just rearranging equation 1. I call this equation what? Equation 3. I'll call that equation 3. What I've done is from equation 1, take this across the equal sign, it will change to negative, and that is what I have in equation 3. Suppose you are asked to change degrees Fahrenheit to degrees Celsius. What you will do is convert that to degrees. It will be your degrees Celsius is given by degrees Fahrenheit minus 32 minus 32 over 1.8. This is equation number 4, I believe. Yeah, this is equation 3. This is equation 2. That's equation 1, and this is equation 4. I'm rearranging this equation. I hope you realize that I take across the equal sign plus 32 is going to change to negative, and then I divide both sides by 1.8, giving me this equation. And this is to change the temperature from degrees Celsius, degrees Fahrenheit to Celsius. We don't have degrees Fahrenheit to Kelvin. We don't have this. So you need to change to degrees Celsius first, all right? And you change to Kelvin. So you need to understand how to navigate the problems relating to temperature conversion. It may have seemed just like, a small info. You do not want to disregard this. Notice that I've derived 4 equations. You have to master, you have to use in problem solving in terms of changing the temperature from one scale to another scale. Here is a conceptual question. It's in the text. Which temperature scale has no negative temperature? It's expected that you can look at here. There is no negative. Here is the negative, here is the negative, and that's what the question is asking, that which scale has no negative temperature. And of course, the correct answer is A, Kelvin. It can be Kelvin. Right. Moving on, let's see. If you are asked to change the temperature from degrees Celsius to Kelvin, in A, this is A, degrees Celsius to Kelvin, means Kelvin equals 273.15 plus degrees Celsius, this will be 273.15 plus 31. We will look at the rules for expressing the final answer with the correct number of significant figures, addition, subtraction. Here, this has no significant, no decimal place, which means our final answer is addition. Subtraction rule, no place of decimal, our final answer will have no place of decimal. Your calculator will give you 304. You try that 304.15. Kelvin, please include the units, just more than what we need. So our final answer will have no decimal place. Remember the units. So in other words, you may see this on the calculator. If it's a multiple choice question, please remember to follow the rules of significant figures. I will talk about that momentarily, but to get you off started with the habit, until you get it, until you commit your memory of observing the rules, calculation, maintaining the correct number of significant figures. If it's a multiple choice, you may have this will be wrong. You may just have to pay attention to. Then lastly, in B, we want to change degrees Celsius to degrees Fahrenheit. And our equation will be Fahrenheit. Degrees Fahrenheit is given by 1.8 times degrees Celsius in parentheses plus 32. We're not going to use the 32 to express our final answer. It's just a constant, but whatever we are given here, multiplication, two significant figures, and also 1.8 is a constant, so 1.8 times 31 plus 32. Your calculator will give you 579.47 degrees Fahrenheit. It's more than what we need in the world of significant figures. Okay, in significant figures, later on you will take note that this is more than what we need. We need to round it off, and because we had two significant figures, we'll have to express our final answer with two significant figures, and this will be 580 degrees Fahrenheit. It will be more apparent once we get to significant figures. This explains sometimes when you attempt end of chapter problem, you look at the answer at the back of the text, and it turns out that something is not really adding up, and you're like, is it a typo or something? It might have to do with this rule of significant figures. So here are just a few examples of temperature conversion. I want you to practice. I know we have a couple end of chapter problems. For those with the text, please do more practice with temperature conversion from one scale to another scale. I assure you, this will be in the quiz. This will be in the midterm exam number 1. This concept will be in the final exam as well. Please, it's very straightforward, simple. Once you master the calculation, the right equation, it will be straightforward. I know this is asynchronous, and somebody may have a question that, will you give us this equation? Yes, I'll give you the formula sheet in the exam. For example, I'll provide the periodic table once we get there. And if there is any other material I feel like you will need for the exam, I will provide for you, okay? But for now, please practice using the 3 equations. Moving forward, let's see prefixes. These are prefixes used to expand or reduce the metric system of measurement. Let's understand, first of all, prefixes. These are used to expand or reduce the base unit of measurement in metric system. Prefixes. Prefixes include kilo. When we say kilo, all right, kilo, okay, we can reduce or increase the base unit meter to kilometer. That means we have increased by 1,000 times. They are the multipliers. Here are the examples of, the prefixes used. Kilo means you increase by 1,000. We multiply by, and they are well defined. These are the prefixes you need to commit to your memory. When we say kilo, that means you are increasing the base unit by 1,000 times. This is the multiplier. Mega, 1,000,000 times. Giga, the billion time. Tera, peta, exa, Deci, you reduce by 10, by 100, that is reducing the pace unit. Milli, micro, take note of the micro, reducing by 1 million, nano, reducing by a billion, and so forth. What I want you to learn is the prefix name and the prefix symbol, as well as the multiplier. By what value are you multiplying the pace unit? Pace unit. I know you have used this before. Some of the times here they are familiar to you. Some are new. In electronics, we use byte to store the information. Your laptop could be 1 terabyte, or it has a capacity of 1 terabyte. That means tera you increase by 10 raised to 12. It could be gigabytes. What is the storage capacity of your cell phone? Some of you may have 256, just to give you the multipliers here. If you are to answer questions such as this, which prefix multiplier is most appropriate for reporting a measurement of 5.57 times 10 to negative 5 meters? The appropriate is closer to micro, and micro we use this. This is the symbol for micro. We just looked at that. This is the symbol for micro, reducing by 10 raised to. This is the multiplier, 10 raised to negative 6. Mega, all right, mega. Ten raised to 6, milli, all right. Ten raised to negative 3, and kilo, this is 10 raised to 3. So you are comparing. The question here is which one is appropriate. You see here, it's just a question of eyeballing and coming up with the best fit. And this is closer to micro, which is 10 raised to negative 6. The correct answer is C. The correct answer is C. Well, let's see. What are the exponential? We want to write the numerical value for the symbols for the prefix here. These are the symbols, and if you look at this, where I'm coming from, that is this right here. Are you able to tag the symbol here with the numerical value? And sometimes you may be asked the name as well for the prefix. So for this is Daisy. This is Daisy, which is times 10 raised to negative 1. Uppercase, this is mega. It's 1 times 10 raised to 6. And P for pico, 10 raised to negative 12. You need to know, all right, you need to know the prefixes given on table. Learn this, table what? Table 1.2. Use flashcard if need be, so that you, when you are given a question such as this, you will be able to answer appropriately. Part P of the learning check, use the appropriate metric prefix to write down the following measurement without using the exponent. In other words, we need to get rid of that. And for A, this is what we need, 4.7 microgram. This is what the question is asking you without, look at this, prefixes to write the following measurement without using the exponent. This is the exponent. This is the exponent. So B for the follow-up question is 1.85 times 10 raised to negative 12. No, negative 12. You want to get rid of the exponent. And this is picometer. I'm just going to write picometer because of the meter here. So you should be able to navigate the prefixes used for that. Now, derived units apart from the units we looked at in mass measurement, volume measurement, length measurement, there are some units which are derived from the pace unit. So here they are derived from the pace unit. You know, the pace unit. Let's say, for example, length, we use miles, for example. And then time is we use maybe hour, all right? We can derive speed or velocity. Speed, this is derived miles per hour. This is a unit which is derived. We also have volume. This is an example. It's going to be meter cubic because you multiply. Or area, which is length times length, will be centimeter cubic, will be kilometer area. We have density, which is the most important thing you need to remember. Density is mass over volume. Here is the mass measurement, which could be in grams, and this could be in ml, grams per ml. We derive that, which I know what is relevant to us is how to determine the volume of an object. Derived unit combination of units, e.g. for cubic centimeters or cubic centimeters is derived from the length for centimeter. Density is a ratio of mass to volume. This is where I have here, and I've given you the units. Units for mass is grams. It's a derived unit. We have other units, all right? Derived could be volume, could be velocity. These are different units, I mean density for different substances. You don't need to memorize these, but sometimes some experiments are designed in such a way that you go to lab, you record the mass, or you take the mass of a known object, determine its volume, and then using the density equation, you can identify an unknown object based on the known given literature values for their densities. If I look here, this is the density of glass, this is the density of H2O. So if I have a known liquid and I determine its density at around 4 degrees Celsius and turn out to be 1.003 significant figures, I know that is H2O, H2O. You don't need to memorize the values on table 4.4, but do you know how to use this equation? I've seen in the past students trying to use this to derive equation for finding density. So here, we just go here, I say density, mass, and volume, so that I'll say density equals to mass over volume. This is equation 1. Or, and there is a multiplication here. What I'm doing is, if I want to find density, it's gonna be mass over what? Over volume. Suppose I want to find mass. Mass will be density times volume. So if I check that across, mass equals to density times volume, and volume equals to mass over density. Mass over density. One thing you need to take note is you should always have pay attention to the units. All right. So here is equation 2. This is equation 3. By rearranging the main equation here, I can come up with two additional equations. So it's not always true that you'll be asked to find the the density of a known substance. You should be able to derive the other equations so that you answer the question appropriately. Let's see, learning check here. The density of benzene at 15 degrees Celsius is 0.87. All right, 87 grams per ml. Calculate the mass of 0.1500 liters of benzene at this temperature. Quite often students miss such problems. They know the equation. I may give you in the exam, but what you will fail to understand is taking note of the units. This is in ml and this is in liters. If you just use the equation, without paying attention to the units, you'll get the wrong answer. And if it is multiple choice, you will pick the wrong answer. So first, you need to change the units, and you'll be expected to know that 1 liter equals to 1,000 or 1,000 ml. So if I want 0.150 liters, we will look at the conversion, dimensional analysis momentarily. And what I'm doing here, I'm changing the volume to ml so that this will move 3, 1, 2, 3, and this will be 150 ml, which is now why we have to reconcile the density with the volume. So mass, from here, density equals to mass over volume. If you multiply by volume, this implies mass equals to density times volume. In this case, is 0.8787 grams per ml times 150 ml, 150 ml, so that ml will cancel with ml. Otherwise, if we had only liters, then the units will not match up. We'll end up with the wrong answer. From here, it's just a question of you plugging in your calculator. And what you'll notice is you'll have 131.805 grams. This is more than what we need. This is more than what we need. We were given 1, 2, 3, 4, and here 1, 2, 3, 4. We didn't use 15 in our calculation, so our final answer should be 4 significant figures. The correct answer is 131.8 grams. We look at the significant figures later on. Pay attention to significant figures. I know you covered this concept before, and that is the correct answer. Take-home message from this learning check is pay attention to the units. Don't just plug in the values and say this is going to work. When you do the Alex assignment, you may come across problem where you need to change the units first before you apply in your calculation. All right, that takes us to section 1.7, the reliability of measurements, significant figures. When we talk about significant figures, these are important figures you need to express your final answer. Remember, I've been dropping some values in the previous example I showed you in the learning check problem. Is because I want to express the final answer with the correct number of significant figures. Before I cover calculation and significant figures, let's see real quick how to count the number of significant figures. These are important digits. In scientific measurement, all right, any measurement consists of certain and uncertain digits. The last digit always is an estimate. So if you look at the last digit here, it's an estimate. And if you look at this 5.213, 5.21, these are certain digits, and the last one is uncertain. Significant figures deal with writing numbers to reflect precision. We will talk about precision, that's more precise, how accurate and reliable the data is. It's important to learn how to record or how to maintain or write down the number of significant figures in your number. And first, rules for sounding or for rounding the significant, counting the significant figures. You always start from left to right. Always start from left to right. Not right to left. That's how you count the significant figures. For example, here, 1, 2, 3, 4. I count from left to right 4 significant figures. Here are the rules. We have about 4 rules. All non-zero digits are significant figures. For example, 198 degrees Fahrenheit. These has 1. This is 1, 2, 3. We found 3 significant figures. Or significant digits is the same thing. They are non-zeros. 1 is a non-zero, 2 is a non-zero. And here in the example, what you see is bolded 2, 8, and 3 are significant. 4, 5, they are significant. Always like just using non-zero digits to be clear about that. Rule number 1 of non-zero, I just pick non-zero digits. Interior zeros, sometimes we call these captive zeros, all right? Interior zeros between non-zero digits are significant. So rule 2 here, I'll call these captive zeros. These are zeros in, this is in, between non-zero digits. We call it captive, it is captured. 4, 0, 0, 0, 8, for example, these are captive zeros right here, captive zeros, all right? And they count as significant interior. They are in between zero digits. This number here, we count 1, 2, 3, 4, 5. This has 5 significant figures. It has 5 significant figures. Zeros in between and zero digits, and leading zeros. Like say 3 here, leading zeros. They are just placeholders. They are just placeholders and they do not count. Here, do not count. How will I know that I need to omit the leading zeros? If I have a number 0.0087 grams, these are leading zeros. You count and then you start counting 1 or 2. This has 2 significant figures. 2 significant figures. If I have a number such as this 0.0008987 milligram, for example, the zeros here do not count 1, 2, 3, 4. This has 4 significant figures. It has 4 significant figures. That's how we count, or we take into account the leading zeros. It leads. The zeros you see rounded here, they do not count. They do not count. This has 1 significant. This has 2 significant figures. However, trailing zeros, these are zeros at the end of a number. For here, you trailing zeros, all right? These are the zeros at the end of a number. Note, count if there is an implied list of decimal. Otherwise, without implied place of decimal, they do not count. So you gotta be careful with the zero. Trailing zeros at the end of a number are categorized as follows. Trailing zeros at the end of the decimal point are always significant. So here, trailing zeros after a decimal point are always significant. You see here, the place of decimal, they count. So 1, 2, 3, 4, 5. This has 5 significant figures. 1, 2, 3, 4, 5. It has 5 significant figures. They come after the place of decimal. It's different from the trailing zeros. Leading zeros. These leading zeros, there is no non-digit zero here, but here, you take note that there are non-zero digits, and then there is place of decimal, and then they count. Now, our trailing zeros before a decimal point and after non-zero digits are always significant, all right? Like, here, they do count. Here, they do count. If there is no place, if there is no implied place of decimal, they do not count. This is ambiguous, so be careful when you are given a number. You just say that it's ambiguous if there is no place of decimal. And then now numbers in scientific notation, this is what it's pretty straightforward. I recommend that anything on the left side of multiplication sign, when a number is expressed in scientific notation, count as significant figures. Look at this. Why do we say two significant? It's because of 1 and 2. 1, 2, 3, 3 is significant. Anything on the left side, it doesn't really matter whether it's zero, how many zeros, so long as it's on the left side of multiplication sign. 4 significant, 1, 2, 3, 4. We have 4 significant. And here, 4 because there is an implied place of decimal. So be careful when handling zero. There are leading zeros, there are trailing zeros, there are captive zeros, and so forth. In this section, you will only be given a number and you are asked to express the number of significant figures. You'll have to know the number of significant figures. Exact numbers, these are numbers obtained from counting, they don't count, all right? Numbers obtained from counting, such as 7 apples. How do I know? I don't need any scale to determine the number of apples. I literally have to count 1, 2, 3, 4. If there are 24 students in a class, I don't need a scale to measure the number of students. All I have to do is count. So numbers such as 24 students, all right, does not mean we have to significant. No, it's they are obtained from counting. We call this exact, all right. I cannot have a student, or we cannot end up with have a student. It doesn't work. They have to be exact and have unlimited. So if you are given a number, you have to use critical thinking, whether it has to do with counting, then that's gonna be like the ambiguous or unlimited number of significant figures. There are numbers from the divination, all right? Divine quantities. What are divine quantities? 1 liter, for example, equals 1,000 what? 1,000 ml. This is it's a definition, divine. 1 hour, for example, equals to 330 that's 600 seconds. Definition, 1 inch equals 2.54 centimeters. These are definition and they are exact as well. They have unlimited number of significant figures. Integral number that are part of the equation. For example, radius equals to radius R is diameter divided by 2. So this number here is an integral part of the equation, and it's exact. It will never change, all right? It will never change. Here is a simple learning check problem. It's just counting the number of significant figures. You will see a mini problem in the homework, in the exam and quiz. Just give it a number and say, how many significant figures do you have here? This has 1, 2, 3, 4. This has 4. So A, this has 4 significant figures. B, the number of significant figures 1, 2, 3, 4, 5. This has 5 significant figures or digits. And lastly, 1, 2, 3, 4, 5, 6. This has 6 significant figures. So chemistry is, mostly they involve calculation for most part. And in math, you do not read math, you practice. So I'll call for practicing and practicing and practicing until you get it. Well, let's see significant figures and calculation. I'll break into two the calculation. There is here, all right, there is addition and subtraction. There is multiplication and division. In calculation, all right, we should not lose or gain any precision during mathematical operation. That's what I did in the previous examples. I had to have more than what is required in terms of significant figures. Otherwise, if I express with all the digits on the screen, chances are we will gain precision or lose precision. Here is calculation for multiplication and division. Here, I will look at the least number of significant figures. For example, 2.33 centimeters times 1.2 centimeters. In my calculator, I'm just gonna grab my calculator and show you what the value is. So 2.33 times 1.2, my calculator is giving me 2.796, and it's got to be centimeters square because I'm multiplying units as well. It has more than what is required in significant figures. For multiplication and division, you look at the number with the least number of significant figures, So this has 3, all right, this has 2. So we need to stop here and see this number right there. It's more than or greater than 5. Greater or equals to 5. We increase the preceding number by 1, and this will be 2.8 centimeters square. This is the correct answer. Please do not think that it's going to be 2.796 centimeters square. For division, it's the same thing. You have to look at the least number of significant figures. So that if you look at these, if you look at the problems here, if we are multiplying 1.052 times 12.054 times This has 4 significant figures. This has 5 significant, 2 significant. So we should round our value or our final answer to 2 significant figures. You gotta stop right here. And if you look at 2 is less than 5, so we drop the non-significant and our final answer is 6.7. 6.7. It also applies to division. This has 5, this has what? This has 3. The final answer should be 3 significant figures, just to give you what's going on in terms of division and multiplication. Look at the what? The least number of significant figures. That's what you need to remember. And let's see, are we going to the next? Yes, addition and subtraction. Here, you look at the least number of places of decimal. Number of decimal places. For example, 10.0 plus 1.829. This will give us 11.829. I just pick up a simple number. This has, if you look at this has 1 decimal place, and this has 3 decimal place. 1, 2, 3. So I'm just gonna stop here. So you do look at this is less than 5. So the final answer for this will be 11.8. I didn't have the units because of 1 place of decimal. If it had no place of decimal, then the final answer will have no place of decimal. So pay attention to that. And that is what is going on here, that this has 1, 2, 3. This has 1, 2. So the final answer should have 2 places of decimal. The 2 is less than 5. So we drop the non-significant and the final answer is 5.41. This has 1 place of decimal. This second number is has 3 places of decimal. The final answer should have 1 place of decimal. This is greater than 5, so we increase the preceding number by 1, leaving us with 5.7. You do the same thing, all right, for subtraction, addition. Now, if you have a combination, you have to follow the order of operation. Some, I know, bracket of division, multiplication, addition, and subtraction. This is the order of operation. You may have your own way of, if you have a mixture of operations, start with what is in bracket first, or then the division, multiplication in that order. Well, I was dropping some numbers, which I know some of you are familiar with. Rounding off, this is something you can read on your own, so that you express your final answer with the correct number of significant figures. Uh, here are examples of rounding off. Let's see what's going on. If you are asked to round the following numbers to 2 significant, this will be 5.4. We increase the preceding. This is less than 5. We just drop 4, 3. This will be 5.4, 5.3. You don't have to go further down to bring the 1 here, and then you bring that. You just have to look the immediate. That is what you need to do. It's just simple concept of rounding. You may also see in the quiz, in the exam, the rounding of concept. Oh, well, I'll leave this one to you. If you want to double check, let's see, in A, I will use my calculator real quick, show you what the value for A will look like. 14.3505. This is plus 2.65, and what I see is 17.0005. It is more than what we need. So this has 2 places of decimal, 4 places of decimal. We should have 2 places of decimal, and that means we're gonna stop right here. It's gonna be 17.00. This is the correct answer. And then B, it is division. So 0.0588 divided by 0.677. What I have here is, this is what I got for B, 0.0868537 666. Sometimes I see this in some lab report. Some lab reports and students think that, oh, this is more precise. This is what I see in a calculator. They expect you, not even in experiment number 1 or a particular experiment, but throughout, all right? But throughout the course, even beyond 10 KM1, you should be able to express your final answer with the correct number of significant figures. So for this, we just went through the rules of significant figures. This has 3 significant figures. This has 1, 2, 3. So 3 significant figures. The trailing zeros, I mean the leading zeros here, do not count. So if we are to count this number of significant figures, these do not count. 1, 2, 3. Right? Look here. This is 5. So 0.0869. And your final answer for B is C, based on significant figures. Significant figures. Well, it's just few examples of rounding off to 19. If you look at the number of significant in parentheses, we took the parentheses, this is what we have. Because of subtraction. So subtraction in parentheses, you know, this is mixed operation. Let me just zoom this so that we all can see clearly. Remember the board mass, we start with the parentheses, and if we are subtracting, we should have 2 places of decimal, and this is the final answer that when we plug in now this calculation, that means our final answer should have 2 places of decimal. I mean 2 places of decimal, 2 significant figures. That's why we have 19 based on what overrides that. Well, some terms you need to understand here are the 2 terms you need to commit to your memory. It relates to data collection in the lab, accuracy and precision. Precision is a measure of how closely individual measurement, underline the word measurement, that is a series of measurement, how close they are together. It's like saying the truth over and over and over, compared to accuracy, which is only looking at one value, how close a measurement, that means one measurement to the what? To the true value. Probably there's a dot here which shows the meaning of accuracy or illustrating what is meant by accuracy and precision. Accuracy refers to how closely an individual measurement or individual measurement agree to one another true value. So here is true or good accuracy, good precision. This is crude precision, but poor accuracy because we want the arrows to be on the bull's eye. Neither is poor precision and poor accuracy. Please remember to make your own notes, differentiate accuracy and what? And precision. Consider the results of 3 students who repeatedly weighed a lead block known to have a true mass of 10.00 grams, indicated by the solid horizontal line on the graph. So these are the three students, their averages, all right? If you are asked which student is accurate, precise, graphically you see student A is inaccurate and imprecise because we are comparing to the true value. You see the mass. Student B is precise. You see, oh, everything is below, is around 9, the average of the true value. So it's precise, but not accurate. Student C is both accurate and precise. Sometimes you may be asked to comment on your final results, maybe average, average mass, or not necessarily, but 3 data points. Maybe if you measure the mass 3 times, will it be accurate or precise for that? So the results of student A are both inaccurate, not close to the true value, and imprecise, not consistent with one another. The results for B are precise, close to one another in value, but inaccurate. C is both. It's a win-win for C. Student C results display little systematic error or random error. They are both accurate and precise. What we mean by precision. Solving problems in chemistry, this is the second to last item I want to look at. This is a factor label method or dimensional analysis, which I know you have used before. We will be using extensively in this course, all right? Many problems you will solve in this course are unit conversion, which means in dimensional, look at this dimensional analysis like that. It means you're gonna be given unit one times what we call conversion factor, nothing like that. To give you unit 2, all right? So you're moving from point A to point B. This is a dimensional analysis way. It's a powerful way of solving problems. Some others call this factor label method. This is conversion factor from equivalent statement. You need to derive that. For example, if you are given an equivalent statement saying that 1 inch is equals to 2.54 centimeters, we can derive two conversion factors here. A, that 2.54 centimeters no, the other way around. This could be 1 inch, 2.54 centimeters. This is equivalent statement. And then conversion, depending on which one you want, conversion factors 2.54 over 1 inch or 1 inch 2.54 centimeters, 2.54 centimeters. Out of this equivalent statement, we can use that so that unit 1, this is what I have here, is the same thing. Given unit times the desired unit so that you reconcile that and then you get, for example, here, if I have 98.0 centimeters equals to how many inches? So the given here is 98.0 centimeters times, I want to get rid of centimeters. I am looking for inches right here. So it's gonna be 1 inch, 2.54, so that you cancel out the units. That's what is represented here. Take note that if I have 98.0 inches, centimeters, which is mark, You set up your conversion factor 98. This is given. So that you cancel that, and then you multiply that. It's gonna give you a different answer. So the point is, how do you set up your equation using this approach to arrive at the final answer? Let's see, how do you convert now 5 days to seconds? If I look at the given value here, it has 3 significant figures. I'll have to record my final answer in 3 significant figures. This has how many? This has, you cancel out or you don't count the leading zeros. All right, 1, 2, 3. It has also 3 significant figures. So both should have 3 significant figures. So how do we go about with that? Some equivalent statement you need to either it's common, for example, how many hours in a day. You should know that. Some you will be given, all right. Some you may have to just use common sense to derive, as in A, for example, we want to move from days to hours, and then from hours to minutes to seconds. And your setup would look like this in A, 5.00 days. We want days here. I need some space, so it's gonna be 1 day, 24 hours times 1 hour, 3600 seconds. You see how I've set up the equation so that hours and hours equal days and days equal. You should have for 32000 seconds. You can also use the scientific notation. You can use the scientific notation for 4.32 times 10 raised to 5 seconds. So this is what I'll do. Take note of how I use 2 conversion factors. Maybe 1 conversion factor, okay? And B, in B, you are expected C somewhere, or you'll be given this 1 mile equals 1.609 kilometers. You may be given that. If I want that change, it's gonna be what? This is 0.0550. So here 1 mile, 1.609 kilometers. A 1,000 miles. So that we cancel, you should have 8. Look at what you may get on your calculator, 495 meters. This is more than what you need. This had 3 significant figures, so this is 3 6 figures, which we found out that it's going to be 8.25 meters. So you notice that the final answer should be expressed with the number of significant figures given in there. That's why this is from, this is the correct number of significant figures for. Sometimes you may, think that you got it right, you used the right equation, your calculator didn't fail you picked the wrong multiple choice and say, why didn't I do well in my first exam? Yet I studied so hard, but you don't practice until you master the concept of significant figures and calculation it might cost you in exam. All right, this is just a general strategy for solving problems. It's just a question of, all right, it's a question of practicing. Like I said, you don't read math, you practice. Some of the conversion factors you have to derive, for example, 1 square inch is equals to 6.45 square centimeter. You will never see this, but it is derived from the given of the literature value for the relationship or equivalent statement for 1 inch and centimeters. You derive those. Other than that, I want you to practice, read more on analyzing and interpreting data in section 1.9 in the text, chapter 1, all right? You will do beginning fall. Experiment number 2 will be introduction to graphing, which you are also expected to interpret data from the graph. You should be able to generate a graph, include the equation of a straight line and so forth. Identify the slope when you are given equation of a straight line, y equals mx plus c, which I know you covered that in the lecture. Other than that, I just want to finish chapter 1 by saying, please do the homework assignment in Alex. It's just more information on interpreting data, which you can read on your own. Try to complete chapter 1 Alex assignment is posted in module 1. Chapter 2 will be posted shortly. Other than that, thank you.